Welcome back. This is another exciting episode of Mr. Takeda Teaches Algebra. I am Mr. Takeda, and I am going to teach you some algebra right now. This is lesson 8.6, the final lesson in the chapter 8. And today we're going to talk about comparing linear, exponential, and quadratic functions. We've dealt with all of these so far, so this shouldn't be too different for you. Let's go. How can you compare the growth rates of linear, exponential, and quadratic functions? Well, we can look at graphs. So, excuse me. So we know the linear function is going to give us a line. That's kind of built into the name. Exponential functions, we know is this type of function here where it'll approach the x-axis but never actually touch it, right? And that's exponential growth. We talked about that for like earthquakes, right? The Richter scale. The variable is actually the exponent right there, right? And then finally, quadratic functions, which we've been dealing with in the last in this chapter here, and we get that parabola. Okay, so line, exponential, and parabola. So if you're given some points here, one way we can do this is to graph the points and tell whether the points appear to represent a linear, exponential, or a quadratic function. I'm not going to take the time on the video to graph all of these because we already know how to graph points, right? Graphing points is easy for us. You could put these, you could either just do this manually or you could do this using the Desmos graphing calculator. But the shape of the line will tell you whether it's linear, exponential, or quadratic. So I'm not going to waste time on the video to do that. We can practice in class a little bit. Let's move on. The main way that we can do this is by looking at differences and ratios of the functions. We know that linear functions, we have first differences. I'll talk about first differences, but we have a constant difference. Exponential functions have that common ratio. We've seen that. Quadratic functions, the second differences are constant. So we'll have to talk about what that means about the second differences being constant. In all cases, the differences of consecutive x values need to be constant. So this only works, of course, when x is increasing at a constant rate. So 1, 2, 3, 4, 5, or 1, 3, 5, 7, 9. So we have a consistent difference, a consistent growth in our x values. Okay, so let's take a look here. Tell whether each of these values represents a linear or exponential or quadratic function. Okay, so what we want to do here, we saw and check our x values here. We're increasing by 1 here each time it looks like. 1, 1, 1, right? Plus 1. Okay, so this is good to go. And what's happening here? 11 to 8 to 5 to 2 to... So it looks like we're subtracting 3 each time. So if we have a common difference here, this is going to turn out to be linear, right? Common difference. We've seen this before. And for B, and again, we have a constant. This is all constant change in our x values. These are all increasing by 1. And what's happening here? 1 to 2 to 4 to 8 to 16. So in this case, this is 1 times 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. So in this case, we have a constant ratio. Constant ratio means that this one's going to be exponential. And we've seen these before. Let's take a look at C. I'm going to extend the page so I can bring this up. Okay, again, our x values have a constant growth rate of 1 there. And so what's happening here is -1 to -2. This is -1. And then -2 to -1 is +1. And then -1 to -2 is plus 3, and negative 2 to negative 7 is plus 5. Now, here's what we mean by second differences. From negative 1 to positive 1, this is a plus 2. From negative 1, from positive 1 to positive 3, it's a plus 2. And from positive 3 to positive 5, it's a plus 2. This is our second difference. And you can see that the second difference here is constant. So this means this is going to be a quadratic. Okay, so second difference is constant, quadratic. So that's new for us. Let's write a function to model data here. First, we have to tell whether this is linear, exponential, or quadratic. Then we're going to write the function. Okay, and I can see here that my x values are increasing by 2, right? But that's constant, so that's okay. And then I can see that my first difference is, they look kind of all over, and I see 12 and 12, which kind of leads me to believe it's going to be a quadratic parabola. It's, turning around. Looks like maybe this is 0, 0. So maybe looks like maybe this is going to be my vertex. Well, let's see here. 12 to 0. This is negative 12, then negative 4, then plus 4, then plus 12. But my second difference here is plus 8. Right? So this is quadratic. This is quadratic. So I can see here I have x-intercepts here. My y values are 0 and 0 here. So I have x-intercepts of 4 and 8. So I'm going to start with y equals a times x minus 4 and x minus 8, using my intercept for that. And then I'm going to use another point to substitute in for x and y, and I'll go ahead and use the 2 and the 12 here. So 12 equals a times 2 minus 4 times 2 minus 8. Okay. So what do we have? 12 equals a times negative 2 times negative 6. So 12 equals a times negative 12. Dividing both sides by negative 12, a will equal 1. Okay, so I'll substitute the value of a to write the function. Well, it's already 1, so my function is just going to end up being y equals x minus 4 times x minus 8. 8 is 1. So I can ignore that. So y equals x squared minus 12x plus 32. Okay, so this is my quadratic function. Lots of work in that one. Lots of work in that one. Let's see what we've got next here. Comparing functions using average rates of change. Over the same interval, the average rate of change of a function increasing quadratically eventually exceeds the average rate of change of a function increasing linearly. So what does that mean? Well, that means a linear has a constant rate of change, and then a quadratic function kind of starts off slow, so it shouldn't be like below that line, but the quadratic function is going to start off kind of slow and then eventually increase. So its rate of change will increase here. It's less here, but then eventually increase and eventually exceeds the linear function. And then over the same interval, the average rate of change of a function increasing exponentially exceeds the average rate of change of a function increasing literally or quadratically. So exponential will be the ones that they start off slower, but they're going to end up faster than either of the linear or quadratics. Okay, so let's take a look here at an example using and interpreting average rates of change. Two social media websites open their memberships to the public. Compare the websites by calculating and interpreting the average rates of change from day 10 to day 20. Predict which website will have more members after 50 days, and then explain. Okay. Website A, so this is, it looks like it's 5, 10, 15, 20, 25. So we're increasing constantly here. It's a consistent rate of change. That's good. And then here, so here we have a graph, but they want us to calculate the average rate of change from day 10 to day 20. So that's going to be, when it says average rate of change, that's going to be linear. That's going to be linear because we're just dealing with 2 points here. So from day 10 to day 20, so I'm going to basically I'm going to calculate my slope using these things here. So 2150 minus 1400 divided by 20 minus 10. And that's going to equal 2150 minus 1400, 750 divided by 10. So it's 75 members per day. 75 members per day. This is for A. Now for B, day 10, looks like we're up. Let me make sure I'm not erasing something. Looks like we're just a little below. What's that going to be? Like 850. And day 20, at day 20, they're at 1800. Okay. So here, 1800 minus 850. And again, that's over 20 minus 10 in 10 days. $950, that's 95 members per day. That's the average rate of change of each of these two sites here. Then the second question says, predict which website will have more members after 50 days. So we can see after 25 days, this one's at 2525, and this one is at 2400. It looks like 2400. So we're about equal after 25 days. We're about equal after 25 days. But this one's increasing. If you look at this, this one's increasing. It looks pretty linear. We have a constant increase every 5 days. This one, though, you can see by the graph, this appears to be either exponential or quadratic. So this one's going to have, this rate is going to increase. So after 50 days, website B is going to have more members. Okay, let me bring that back up there. So average rate of change over the time period specified, and then this one will have more because this is exponential or quadratic. Okay, that's it. That's the end of the chapter, and I will see you in class. Bye-bye.